We do have a code of conduct. You can find it on the website at chip.org/pages/conduct. Reading material. Basically, the gist is don't be a jerk. And I'd like to remind everyone that there is no pandemic. People have very degrees of comfort around being near other people as a result. Please be mindful of everyone's personal space. We'd like to thank our sponsors because they make it possible for us to have meetings, beer and pizza, and we're very appreciative. And 17 also for hosting us tonight. So for anyone who's not familiar, ChiPy, Python focused community, that started off as a group of people meeting in bars, and it's grown to meet up with 6,000 members since 2003. And we're one of the largest and most active local Python users in the country. I'd like to introduce our board members who are here. I think that's basically me, Joe, and Ross. In addition to our other meeting, we have other initiatives. We got a project night, and then we also build their websites. We have a buddy mentorship program where if you want to learn a skill, you can sign up to be mentored, and if you know how to teach a skill, you can also sign up and mentor someone else to learn that. We have the Python Lunchbreak SIG, the algorithm SIG, and we also have a job board on our website, chip.org/job. If you're looking for a job, you can go there. Also, if you're looking to hire a programmer, please go there and get jobs. You can find us online at join.org. We have Slack. Great way to discuss things, people, get along projects. Thanks to our Twitter, Python, and of course, we have ChiPy.org. With that, we have two talks scheduled for tonight. I'd like to hand it over to our first presenter, Carson.
All right. Thank you. Get that out of this. So, hope nobody expected a polished talk with PowerPoints on it. That's not happening. What is happening is some show and tell and lots of questions. Because anytime I show anybody this stuff, it's so. First, some big picture stuff. Python. What is Python? A bunch of answers to that, and I believe the correct answer is Python is the definition of a language. Definition means not the implementation. So the documentation is sort of a cloudy notion of this source code makes this stuff happen somehow is Python. You all probably have some flavor of Python installed on some machine you use. It's probably CPython. Just because it was written in C. And that's the implementation that we all know and love, and you get it from python.org and download. There's also Python, which is Python that runs JVM Java something environment, which does the same thing as Python, but it's written in Java instead of C. Relate. The guy that wants to see your talk. guy walks in the door. Anyway, there's also MicroPython, which it took me a while to understand how similar it was and real it was to all the other Pythons. And really its claim to fame is it runs in a much more constricted environment. Like this little thing, there's an LM32 F415 something chip. Try to buy this chip, they'll say estimated delivery 18 months. Nobody buying this chip anymore. But there's a little bit of flash RAM on here and something. And if you take this thing, solder it to a bigger board like this, and see the one back here, it has USB ports jacked into it. Plug it into your laptop, you'll see a USB flash drive and storage device, whatever. Which is not really Python, but that's part of the MicroPython thing. And this is where it gets kind of fuzzy. So what is Python? So whatever. Also, I'm going to skip over a bunch of stuff. Like, how does that happen? Well, ask the guy that wrote MicroPython. It's a bunch of C code. You compile it to run on the microprocessor. You run the utilities to take the code, compile it on the microprocessor, give the microprocessor the power, and it boots Python. Sure, I love the question.
So it's bare metal.
Yes, just going to get to that. There's no operating system. There's no boot loader from Linux, Windows, nothing. It's just the thing that is Python starts to run. And that is both amazing and simple at the same time. The amazing thing is that, well, Python doesn't really need much of an operating system to survive. It needs some sort of storage so that when you say import food, something happens. And it doesn't necessarily have to be asked the operating system for a file. It just has to, like, this wad of Python modules has the label food next to it, it's stored somewhere. And this thing called Python has to be like, give me. And then it's sort of like, well, so now on a food namespace and this wad of code, do their Python, just like import food in any which, see, part of my little journey here is I find a lot of these abstractions or whatever you want to call it, like described, kind of enlightening when you realize, oh, the import module, when you type import something, that does stuff. Just because you think you know what it does, you might want to like settle down on that a little bit and realize, well, it does what it needs to do. Don't worry about how. Anyway, so power this thing up. It runs Python. It looks in the file system of USB drive or code.py and runs. So once again, there's no operating system, so there's no like startup script or anything. It's Python VM as part of its startup or whatever. It does all the things any other Python does. Like, I looked through this before and now I'm going to explain what all the Python VM does as it initializes. Anyway. Eventually it gets around to, okay, time to do something useful, code.py, run it. In this case, code.py brings up some cool stuff that I've got laid out. And this is kind of like what robots are built out of. Or maybe I should just say, this is what robots are built out of. Got little switches so that something can see like when it gets pushed up against it. And we've got a little motor here so we can move things around. We've got some input devices here so that somehow this robot has an idea that it needs to do something. I hit this button. I can't actually see the button. How does that? Little button. Gotta go back home. All right. So how did all of that happen? So post.py looks on the storage device for a JSON file. JSON file is the definition of this button. What's this button do?
No labels.
Yeah, so I'm going to say it moves it that way. That's not quite, oh yeah, it adds one to the current position. There. By the way, this is Andrew Wickett. He actually built all of this. I wrote the program. Andrew.
Well, I mean, you can wire up exactly what this thing is.
I'll get to it in a moment. So, this JSON file I mentioned, this is the GUI that makes the JSON file. So, he's going to wire some I/O together. It's basically like how this came about. So, while he's doing that, question time, yeah.
So like, one thing I understand about Python is that a lot of it's not all language systems, syscalls, and a lot of the file system interactions are with syscalls, but you don't have operators.
You have to write that yourself.
Or basically everything just lives in the heap.
Okay.
So it's either in the heap or you're actually like, there's kind of a micro OS in there sort of that will give you some sys type calls if you want to open a file from Flash or from an SD card or something like that, then you kind of tunnel through that and you have your open file that you can now use.
Well, hang on, I'm going to dispute you on this.
Yeah.
Because everything you just described is what MicroPython is. That is, like, MicroPython's not calling out to anything. It's not going to call out.
Hard Flash.
There's always that.
Well, the MicroPython actually has its inodes classes.
Well, careful with inodes and file system are an implementation. So, like, it might be a fat file system, which I don't think that is.
When was the emulated?
So then what would, so I guess, so like you can have like within MicroPython, like code like the pipeline environment, it's abstracted away, so like you just ST out, ST arrow.
So what this the MicroPython does for that is, well, you can jack a serial terminal into it. There's your I/O. So all of these standard I/O that you just talked about exists in a very limited way of, well, you don't get to redirect it anywhere. It's just, here's a USB serial port, a terminal.
A TTL.
Yeah, it is a TTY.
Yeah. So run your USB cable from here to here, run your favorite terminal program, screen, TO, buddy, and then you can see MicroPython's output. You can feed things into its input.
Or shell.
Yeah, if you get the whole REPL shell. Got more? Come back more.
Some just try to think about it.
Yeah.
Like,
I do find it kind of mind blowing.
like you, it seems like you have to compile MicroPython directly.
Some of it does.
I feel like the person who has to do it, probably have to buy inline, has to write it in assembly.
Sure.
Let's see.
Yeah, it's a really good one. It just won't go.
I'm pretty sure it still is, you have Python code and then you end up with some kind of like code.
Yeah, something that actually runs that like
Yeah.
makes it real.
Correct, yeah. So that whole stack still.
Well, now we're getting into the Python.py code run versus MicroPython.
A lot of the things that you'd be looking for that you're used to in CPython will also exist. Strings, list comprehensions, all kinds of comprehensions.
Another good one is open file, which you kind of, I mean, I said file as if like a file is going to appear on a hard disk, right? It's not really a hard disk, there's flash, which, okay, we've all learned that USB disks are thumb drive disks, but calling it a file system, pushy, it gets dicey. Is this a file system or is it a key value store? And the good news is it doesn't really matter. The guy, and I should have like given some credits on my screen here. By the way, MicroPython is written by a guy who's procrastinating and did not want to do his PhD. Like, I want to do anything but this. And he decided I'm going to write Python. Then when I'm done writing MicroPython, I'll get back to my PhD thesis, whatever. It might have been he wanted MicroPython part of this PhD. I don't know, but it's kind of hilarious that it was a definite like procrastination effort. Talk about this?
Sure.
All right.
One sec.
So.
Oh, just there's a lot of clanking in the background, so just make sure to speak up. You know.
Okay. There's a bunch of boards all mounted onto a DIN rail. 1, 2, 3, 4, 5, here's okay, take a pass. So, take a look at it, send it on its way real quick.
So that one there is a DC motor driver.
Somewhere on the board is this little brain, it's the microcontroller, the flash RAM, and Python. And along the edges of this board are a bunch of little connectors. You take this board, stick it on that board, and solder up all these connectors. And now it can talk to the chips on that board. And that's a DC motor controller. Okay, good. One of the boards here. So one of these boards is pinch on there. It has two little graphs, 2 buttons, and pot A and pot B. Pots are variable resistors. You turn them, the resistance changes. The electronics on the board read the amount of resistance and then make that available to MicroPython. Anyway, so what Andrew's done here, so this GUI, kind of a proof of concept. It could work. That's much better. On my board. So pot A goes to position set. Pot A also goes to the second row of digits on the 7-second display. The position get goes to the first one. Thank you. So we've got these two things here, which are all now upside down. I want to see you guys do that. So what Andrew did was he turned pot A, that set the position and changed the digits. Now, this line stop thing, because there's a saw, like carpenter saw called the tiger stop. So we're going to make our own. We're going to call it the line stop. Turn the knob to where you want the saw blade, and it moves the piece of wood until it's lined up. And you cut it. Anyway, it takes real time for that motor to like do what you told it to. So even though you set the position, you still have to wait for the little stepper motor to work its way over. So these two things won't be the same immediately, but as the thing walks across, this display ends up equaling that. These two things kind of the same, but looks like segment there, hardware stops. Anyway, stuff is kind of cool, but this is supposed to be a talk about MicroPython. Oh, and Canvas. So, once again, each one of these boards has this little chip on it. Each one of it, when it boots up, it reads its config file. So this knows when somebody tells me to display digits, I display digits. And that's kind of defined in a subset of the JSON that comes out of this. Someone board.
I have one, but, what is, how is the, how is, I know like resistance changes, how is voltage and measured? It's basically a cheaper value.
Built into these chips is a ADC, analog to digital converter, and you just ask it for whatever it produces, and we'll give it back to you in a 10 or 12 minutes.
I think the important thing is there's a MicroPython library to talk to the.
Yeah, MicroPython library will talk to the hardware. The hardware itself has some built-in hardware that will actually do the actual conversion.
So like the same, API format.
There's a bunch.
Okay. Like I think I work with like Microsoft.
Yeah, well, that's the kind of nice thing about MicroPython is across your different hardware spectrums. From the Python side, everything kind of looks the same.
And the two is each node in Microsoft on that loop, more or less, scheduling.
That's a limitation. Or details.
Let me answer that. Also, let's back up. First question was, how does MicroPython get a number out of the digit? And once again, the answer is, well, there's some hardware that changes the resistance value into some bits. Yeah. And then, ChiPy on the microprocessor, or is that already in the microprocessor?
Well,
Made available.
ChiPy are the pins exposed to the output inside this hardware.
Yeah. One of the things I still have trouble with, like, believing, is that these little electrical connectors on here map to bits that live inside the computer. So if there's voltage on it, the bit's a 1. If there's not voltage on it, then the bit is a 0.
How fast is that communication from bit to the physical application?
Not instant.
Is that why it's slow?
It's not slow.
I'm not saying, I'm saying, is it slow because that whole process has to occur, and that's why it's moving slow?
Oh, no. The reason so there's two reasons why this is moving slow. My code sucks. I don't care at all about acceleration curves. And this is purely for demonstration. So once I got it moving, I'm like, I'm done. This motor is capable of whipping that thing across really fast. But you don't want to just tell it to go to 0 to max immediately because it will like miss some beats and then you don't know where it is or something. So I just a really like clunky Python loop of move it once. Did you move? Yeah, okay. And if you hear it kind of buzzing, each one of those is the motor moving a well-defined step.
Isn't there like, sorry to interrupt, isn't there like a way to see how fast that motor can run? Then couldn't you tell the difference from each?
So the two answers to this is motor has a dash.
I was just gonna say, if you want to do that, you have to have a full-on high control, like a control system running on the chip
That's not.
in order to spin it accurately.
But if you know what you're doing within that, like, amount of speed, then you can just put it in MicroPython. Say, okay, get the data sheet, understand how much you can go out there.
So essentially over here, there's a stepper controller driver, and to move the motor each step, you only just need to send a pulse to the driver, and the driver will take care of all of the PWM stuff to set the motor to go through its little micro steps.
Yeah. So you mentioned PWM. Do you know Python has like a standard, or MicroPython has a standard library for like UART, SPI, all that?
Yeah, all of the above.
They have all
as
of that?
well. Yeah.
That's awesome.
On the, just to stick on the stepper motor driver here really quick. How can we time pulses and do all this? This kind of moves it out of the realm of Python. Some of the other hardware that are done utilizes the I squared S bus, and so then you can basically dump out basically kind of like a WAV file into a shift register and get kilohertz, very nice pulses to drive something like this. The way that
So that's the way it goes to PWM, is what you're saying? Is that like, is it the pulse that's beginning and moving into the registers?
Well, PWM is a little bit different, at least in my mind, because it's like
It's the frequency change, yeah.
yeah, it's frequency, but like to drive a stepper motor, you want pulses at very specific intervals,
Okay.
and the intervals are not the same, so you're changing it all of the time.
But PWM, the frequency is fixed, but how long it's on or off is what varies.
Yeah, the duty cycle.
Yeah, the duty cycle, but the frequency is always the same.
The frequency is whatever you set it at. So
Well,
it's
I'm
variable
saying
frequency and duty.
If you like looked at a PWM signal, like the places where it's going high are always spaced out the same apart. But how long is high for is all.
Correct.
Yes, they're not like that. It's always the same. If I put it down this far, it has to go. I think it's like. And then you change
The speed.
Oh,
Yeah, which are level. But I think his point is that he was just trying to get it to move.
Sorry.
Yeah,
I'm so sorry.
He moved with fine tuning controls.
Anyway, some disclosure here. Half of what you guys just said, I just kind of trust. Like, yep, all right. Sure, Al's moving because the code says it. All right. And he needed some help with Python, so that's why I'm up here.
How does it then get cold?
I think that's, I wrote it with this stuff.
Yeah, I mean, there is asyncio if you want to play with that.
Actually,
that exists.
now that I've given it enough thought, MicroPython, it's really this context, not now, and I wrote a while
So
It works the way you build it.
basically, there is no like operating system scheduler that.
There is no operating system.
Okay, so it's literally just, you build your own scheduler.
But there are interrupts. I don't want to touch interrupts.
Yeah.
Yeah, well, interrupts just come with the hardware itself.
Like, if you hit the microprocessor, one of these pins on the microprocessor, you don't like jump to some other code.
So it's based, I mean, like the lowest, what, all you need is to have like one scheduler, or two pulse schedules. And then we're basically pointer is set jump back and forth. That's how some asynchronous Python sliders will realize it. And, but it doesn't come with that, you have to build it yourself.
Yeah, you'd have to build that yourself. The interrupts.
Yeah, you have to build that. But again, the hardware interrupts are when an electrical signal hooks the CPU, it'll stop what it's doing code-wise and jump to some other block of code.
So it'll come up and then you'll have some kind of callback function tied to this interrupt. It will say,
Or you don't and crash.
I guess you can have a two schedule like that.
mean, that's, if you can write it in Python, sure. Which I think is what you're saying.
So like,
Build your own interrupt.
so like, let's get it like this. So you're basically directly interfacing with the load up the memory of the CPU and your well, and like how can you like modify this directly?
Like on the hardware itself. Yes.
So it's in line.
Yeah, just inline assemblies, like.
So one of the nifty things about MicroPython is you can just jam assembly code inline to your Python code. Sure. Once again, gives me a headache.
You do it in C, always over
Alright. Yeah. All of a sudden, you're telling the microprocessor, do this, other thing. Ignore all of these pointers and counters, whatever you got, whatever the Python VM is doing.
Look at one more in
You get the virtual machine that's pretty well behaved, but you can circumvent that and just fiddle with the microprocessor directly. And then it returns from that, goes back to Python, doing its Python thing. Python has no idea what just happened. So hopefully you don't mess things up, but it's definitely like shoot yourself in the foot, blow your legs off, whatever you want to do.
So we were just have a small discussion, we just wanted to confirm that when you plug in the object within the motherboard, it just goes to Python.
Wait. What motherboard?
Whatever, like in the beginning you said, when you plug this piece into the computer, it goes out to Python to get all this information, talk to it directly.
I'm gonna walk this back just because. So that's the microprocessor with a little bit of RAM. Oh, forgot about this.
So this also is running MicroPython. And like, there's no larger computer hooked up to it, but when you turn it on, whatever script you have just starts running.
And then it's pulling from Python.
Well, it is Python. Like, there is no OS that it goes through, it just, yeah, just main.py. So when this thing first boots on, it's going to look in its file system or whatever, and it's going to look for a file called main.py. Well, first it goes boot.py and then main.py. And whatever you have there, it will just begin executing.
So it's just gonna do that execution all the way.
Correct.
If you write it in as a continuous loop.
Correct, yeah. If you don't have it as a loop, it will run through your script, and when you get down to the bottom, it will just dump you right back in the
So in theory, you could write an operating system.
Yeah, I mean, it's Python. At the end of the day, it's just Python, and it behaves very similar to CPy. In any way that you would be, unless you're really, really getting down into the stuff, it's very similar.
Thank you.
All right.
Oh, you crashed.
So, by the way, does anybody want to actually see Python code that like reads JSON, parses JSON, while through? Sure.
Unless it's like top
I mean, I feel obligated to show Python code. It's a Python thing, right? I feel like these other things are way more interesting. Maybe the other presenter will show up when I'm off of it. Also, I'm going to take a moment to talk about Canvas. Just because. You want to see the GUI again? Anyway, so microprocessor here, the LM32405. Right?
STM32.
It includes CAN bus protocol, not transceivers. Algorithm?
Well, it has built into it a CAN bus controller.
Yeah. Okay, power control. What it doesn't have is the transceivers that take the CAN bus voltages and drop them down to something that won't blow this up and make smoke.
What is CAN bus?
Yeah, good question.
Things are hard and all that, right?
CAN bus is a communication protocol that you have in your automobiles. And it's a shared bus technology, which is kind of neat because now you can have multiple controllers or something all in one bus. And the kind of neat thing about it is they can all talk at the same time, but there's a way that priority is preferred to different messages over other messages, and that's handled kind of instantly by the CAN bus protocols.
So everybody knows what Ethernet is. The Ethernet cable, cat data, watch cat videos. It's another way of shooting data over a wire that has pros and cons. So that, like, first of all, it's only a pair of wires. One pair, not two pairs. All of these things are just sort of like clamped onto those two wires. Anything can blurt out its message and it goes both ways. The wires light up and everything listening immediately gets the message. Repeating what he said. There might be some gaps I'm going to fill. What you can't do with Ethernet is run it like a mile. Cat 5, Cat 6, all that stuff has like 100 feet or 100 meters or something like that. And then the signal degrades to where it's unusable. This stuff,
I think it was somewhere around that.
yeah. So, you know, you've got a barbed wire fence with two runs of wire on it, clip, and that probably can be made to work. Also, if the thing runs past an elevator motor, big electric motor that work and shoots out a bunch of interference all the time, somehow this CAN bus protocol is resilient to ignore that. Here's your data.
Because you got a car, shine things inside of it.
Or you got,
You want your ABS.
yeah,
It's pretty important.
your powers, and you're trying to manufacture cars. What I've learned recently, a bunch of turkeys grab pieces of metal and shove it into the assembly line, kind of like Terminator, grabbing stuff and doing stuff. Those all have motors. Well, maybe they're called motors. Anyway, it's a very hostile environment for delicate communication protocols. Also, forward motor plant, big place that might be stretched out and once again, not appropriate for more delicate.
Sorry to backtrack.
Yeah, sure.
Going back to, what was it in CAN?
CAN, C-A-N, bus.
CAN bus.
Yeah.
You said it has a limitation of 1 mile. Holy snap.
Yeah, it's a spec. So you get, you can only put so much bandwidth through at different lengths. They're proportional. So if you have a shorter, like it's with total length of the bus, the shorter you are, the higher your baud rate can be. So at a mile, you have kind of low baud rate, but like,
So you probably noticed RJ11 connectors, I think, on these things. So all of these little things have a little RJ11 in and out, linking these all together. And the reason it's this short is because, well, I put it in that cardboard box and walk around trying to make this stuff work, and then showing people because it's kind of cool. But yeah, you could have a big old spool of this stuff, whatever. It's yeah.
How much information can it hold?
say again?
How much bandwidth can it hold?
So the fastest baud rate in spec is 1 million baud. That's how, so I can't think of the proper term. What's that?
It says 300 was the character that we, like, every second or so.
Yeah, I mean, it's not super fast.
It's
It's,
so I know that I'm watching it here.
So,
yeah, it's 1 million per bar.
yeah, 1 megabit.
One way.
Thank you.
Now, to be fair, you're not gonna get that over a mile. That's spec if your things are approximately close. And part of this has to do with the collision detection. You need time for the electrical signal to propagate down and come back, because if something else says, screw you and your message, I have priority, here it is. This thing needs to like have enough time to learn, oh, my message didn't make it. Something else stepped on it, I gotta do it again. And the time it takes for an electrical pulse, like, which is like speed of light through copper, whatever that means.
Some mathematical constant.
Yeah, so like just the physical length of the wire and the way electrical signals do whatever magic makes electrical signals do the thing over wire. The length of the wire matters.
300,000 kilometers per hour.
Could you link fiber, could you put fiber in instead of copper?
Well, I mean, CAN bus itself, the spec is just a differential pair.
Sorry, could you repeat that?
CAN bus, the spec is just a differential pair.
So
The reason you couldn't put it over fiber, but it would be out of the specification of the
Yeah,
sure.
I mean, that is kind of interesting. If you could have light shine into a fiber and kind of go everywhere, up and down.
That's where you would want like data to be quality, you want quality, so you know you could get it, you fiber, right?
My hunch here is that like in order to transition an electrical signal to light, you need to light up a diode relay or whatever. That has latency, right? It's not immediately blinking. It's let you warm up and start radiating light, and that's probably just going to kill any sort of performance, whatever. Once again, it's kind of outside my like thing. You hang out with this guy long enough, you learn stuff. All right. Oh yeah. I missed some things earlier on when I was trying to talk abstractly about MicroPython. Now for your commercial grade, Adafruit product 3333, Circuit Playground Express. Also has a microprocessor on it. Kinda runs MicroPython, but not really. The scoop here is Adafruit said, well, we like MicroPython because we can run it on a little $25 board, a bunch of NeoPixels, accelerometer, chip sensor, microphone, all the things on the board. But MicroPython's got some rough edges. It's not exactly the same as CPython that everybody loves. So they forked it and said, let's make it a little more the same. So if you learn Python on this thing, you can transition over to, and now I'm writing websites in Django. Python-ish.
From my understanding, it's more, it's not that it's not close to CPython, it's that differences between boards in MicroPython, you could add some different, like this Python. Like the way that MicroPython decides to talk to the hardware would be different across boards, and they wanted, CircuitPython wanted their across boards, whatever, to have the same allocated code to talk to the hardware. It's less.
Adafruit has a bunch of products. They wanted all of the Python on all their product lines. They gave the same. In MicroPython, CircuitPython on Adafruit's products, the way you talk to NeoPixels is all like the same syntax, API, whatever you want to call it. Import this thing, set LED1 equal to 255 and 255 with your RGB thing for what, regardless of what board / NeoPixel
interface going on. MicroPython sort of jams it into the developer spaces. It's different hardware, different. And that's so that you can optimize, get the most out of the hardware.
So this is the STM board to get at your ADC question. And this has an ESP32. And their analog to digital converters that they have built in are different. So while it's very similar going between these two, you can't just like kind of take code from one and just whack it right into some other script and run it. They're a little bit different. Like when you get way down on the hardware side and initializing the hardware, they're going to be a little bit different.
You just have to write more fiddly code to know what's going on.
There's like low-level serialization. You have
I heard some initial.
Yeah. So I can't remember what it is on the STM side, but over on the ESP32 side, now you have whether you want it to be how many bits wide do you want it to come in as, are you measuring from 0 to 2 volts or 3 volts, or I can't remember what what's actually called, but like what's your range that you want to measure from to, and that doesn't exist on this one, so like there's just some extra code.
I mean, if you want to write portable code, then you or me or the person who wants this thing has to write some abstraction layer. And as soon as you write that abstraction layer, you're like, you know, the common, you know, you expose the things that are common across them. If this one has a feature that that one doesn't have, well, you don't get that feature. So that's the difference between MicroPython and CircuitPython. I will also say that this thing I saw at a conference in Detroit, and it has changed my life. Anytime anybody says, "Hey, Carl, teach me how to program," you all know how to program, so I'm not going to teach you how to program. But my previous experience was, oh, geez, all right, yeah, I'm going to teach you some stuff. I like that. So first, let me give you a 20-minute interview to find out where you're at. And give you another 20-minute interview to figure out like what direction you maybe want to go, so I can teach you something interesting. And then we're going to spend hours setting up your laptop and doing project management tutorials and talk about GitHub. And like 3 hours later, no Python has been taught. The person knows. Okay. This, you jack it into a USB battery. It runs code.com. If you don't believe me, I'll show you later. And normally I jack this into a battery right into the USB cable. When you touch the touch sensors, the neopixels light up. You hand the thing to a person, it hits their hand, then start lighting up, and they're like, ooh, pretty. They're immediately engaged. Within 5 minutes, you jack the thing into a laptop, the code.py file, you can edit it. You can look a little wilder if you touch this, make the LED that color. It's like 15 lines of Python code. So you can immediately take it in and get the idea of, all right, touch this, light goes on. Code says, touch this, light goes on. 5 minutes, they're learning Python. And then because it's on a jerk, and I don't have any way to turn the lights off, they would say, well, how do you turn the lights off? And now we're teaching them Python. Well, let's change the code. Push this button to turn all the lights on. It's like the next 5 minutes. Within 10 minutes, they absorb what it means to be a program and are modifying it. So there's your answer to that. Yeah, for this little commercial break. All right, on to FPGAs. We'll get back to this in case anybody has been hiding any questions here. So we can talk about microcontrollers. Microcontrollers are integrated circuit chips that were probably made in TSMC, Taiwan, manufactured. Yes. Company in Taiwan, they make all the chips. And Taiwan, semiconductor manufacturing company. Corporation. Anyway, this board has an FPGA. It is also an integrated circuit, but it needs firmware loaded into it or something before it will do anything useful. Microcontrollers, if you plug them in, they do something useful. That's what they were built to do, is be a microcontroller. RAM, you plug it in, it's meant to do something useful. The motor control chips, they were built to do something useful. FPGAs were built to be defined, to do something useful. The key here is you have to take some source code on your laptop, define what it is you want this thing to do, load this stuff in here, and it does it. Which sounds a lot like a program. It's like lower level, because instead of writing like while loops and all that stuff, you're putting together logic gates. These two go in, one comes out. That's either an AND gate or an OR gate or something. One in, the opposite comes out. That's like an XOR gate or something. You've got like 7 things to assemble into and do something useful. Or one internet, go down.
There you go.
Boy, big gallery. Sorry. Not this question. Anyway, FPGAs. So you can download things from the internet where people have uploaded their open source, make the FPGA do something useful. For instance, someone had, or a bunch of people have defined a microcontroller. This is one microcontroller which you can't buy right now. This is another microcontroller which you can't buy. What's the one you've got going on with them? EM32. The third microcontroller, you can buy all these things. Each one of them has its own
Way of interpreting bytes to do stuff.
yeah. Instructions. Bunch of byte comes in, and the data sheet says, here's what's going to happen. So there's another microcontroller thing you can load into an FPGA. In fact, there's a whole bunch of them. RISC-V is like the open source CPU, whatever definition. Grab that, grab all the software that's on your laptop, crunch, 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 upload it into this thing, and then it is that chip. Also, there's a bunch of space left over in this FPGA thing. I don't think it's taking this out of the box, but like a picture of a board.
So it's like a programmable architecture kind of thing?
Correct. Yes. Careful with the programming. I mean,
The level of.
because to me, programming is high-level languages. This is the opposite of high-level languages. It's like about as low as you can get. Like the lower is, well, let's just take some transistors and start soldering them together. So
A little higher.
here's the board. This little diagonal chip on here. That's the FPGA chip. The reason this board exists is prototyping. We want to sell a bunch of these chips. We need people to be able to play with these chips. We're going to stick this chip on board with a whole bunch of I/O and some switches and some LEDs, Ethernet port, USB port, power thing, la 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 la. Just pack it up, and now you can buy this board for $150. I don't know. Follow the tutorial on the internet. Now, hang on, because here's where we go on a roller coaster. The tutorial on the internet. You'll download all of the C code that is Linux. You'll download GCC. You'll download a patch to GCC. You will download a microprocessor that doesn't actually exist in the real world. You're downloading it. You download some. The thing that tells Linux what kind of device tree files, what sort of hardware is Linux living in. Somewhere around 20 steps later, this FPGA chip is both chip, the Linux operating system, some RAM, some file system-like thing, and some serial I/O so that if you jack your
USB cable back into here, remember we were talking about serial ports and everything. You'll get a login prompt, you type root, enter, and it's like, all right, here's your prompt. It's like, this thing is running Linux. Not only is there no operating system, no CPU, there's no NU. So it was all like downloaded and shoved onto this thing. So, and now to tie it into this thing. Well, that tutorial I just described to you hasn't worked in a year. Some libc thing broke, it all fell over. The new tutorial, get rid of Linux, put in MicroPython. So you download the compiler, you download the CPU thing, you download the patch to the compiler to make it work on the CPU, you download the MicroPython, you download the port of MicroPython to the make-believe CPU or whatever. Get all that stuff working, and lo and behold, you've got a REPL prompt, you can run code.py or whatever on this thing. Go, what's up?
Does that introduce a lot of overhead, or is that not the point because it's
So
prototyping board?
you will never get something running as fast as whatever the current state of the art CPU is. We have the i11 or 13. Like, if you try and make a CPU on this, it competes with whatever Intel's current top line, you'll lose. But so that I think kind of answers your question. But if you back down a couple generations, you know, like I don't know, Pentium or whatever, you can get one of these that will perform comparably to a Pentium. Now, that's because this was made a decade after the Pentium, so technology sort of caught up and let those two be equivalent. So you'll end up with a 800 megahertz processor on this $150 board. Now you can't buy an i whatever for $150. The whole apples to apples comparison.
And even then, you still have to hook a motherboard up to it.
Yeah, that's a whole different. So anyway, yeah, they're like, pretty sure the answer to your question is yes, you have performance penalty running stuff on it. But you can prototype, you can reflash the FPGA over and over and over. Fiddle with like, I don't like the way this processor works. I needed to have extra instructions or something. Fork the processor definition, compile your stuff in, maybe give it back, maybe not, whatever. And then you got your own processor. Sneak in another thing. Actually, this is it. So, since we've got some people here, I got a few of these to give out. All right, I showed you this big old board, big and clunky. My friend Tim and some other smart people came up with this whole little like, I know, let's make a little PC board that fits in your USB port. Okay, this one, the symbols are hard to see the FPGA chip on it, or it makes it hard to see, you can't really see the FPGA chip on it, because it's so damn small. Shove these things into the cases. I'm trying to pop one out of the case. There we go.
Period this section or something?
A little bigger than that.
All right, so pass it around. One of the little chips on it, it doesn't really matter because they're all like this big. It's the FPGA. And you can also do all of this blah, 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 and then MicroPython is running on that. Which, and then the bill of the cost of one of those is $20. So this thing I said $150, whatever. Those things, $20. Quantity. If you buy in quantity 1,000, $5 or something. My friend Tim buys quantity 1,000. That's why he gives me a bunch to give out to people. So there you go. That's that thing around. You can see how ridiculous this thing is. So in case you're wondering, like, how much hardware do you need to run Python? Okay. Yeah, any questions about FPGAs and all that nonsense I just talked about?
So like, let's say you have a standardized serialization protocol, you can literally, it comes in basically, let's say you have like 32-bit pins, like concurrent, and then you can basically do the logic, like almost an analog.
I know what you're saying, yes, absolutely. You've got 32 GPIO pins, you can put 32 gates up to those, and whatever it takes to lock that into a 32-bit register. And if you've got a microcontroller that's, the microcontroller light set up, that thing's ready to go. It all is one clock cycle. Oh, yeah.
You work for a hedge fund, like doing Qs,
Yeah, they do.
VGA, doing something.
Yeah, I kind of glossed over that. All of these gates, they all sort of operate every clock cycle. So your Python code, like, you know, 8 goes 1, like 8 million CPU cycles before it gets on to the next thing.
Yeah.
Everything you do with this FPGA thing, you put the clock out to it, it's like gigahertz or something or other, something divided by 2, things, whatever the heck. And when that clock pulses, all of the transistors are like, oh look, we're doing stuff now. And it like changes state in a clock. Yeah. So, some things, like, well, there can be more than one clock or something, and you need to wait for the two things to synchronize. I don't do that.
Literally just go like, let's say 16 GPIOs, have it and gates, have it output, and they use like a certain type of.
Yeah,
Well, that just is what FPGA is. You're like programming the gates themselves. Your field programmable gate.
yeah.
Cool. And then you do the flip flop.
Yeah. So anyway, the tieback here is if anybody wants to like grind through a tutorial that gets MicroPython running on that, I've got 3 of them. All right, so figure out some way. I don't know. Bring tickets for drawings.
Roll the dice. Throw the dice on one of them.
What's that?
Throw the dice on one of the things.
All right. I think I've run out of things to talk about. I never showed the Python show. The talk description has the GitHub. If you actually want to see how to make MicroPython talk to Canvas the way I did, or want to see how did I do import JSON, parse JSON.
I guess to close it up, I can just talk about what this thing is.
Yeah.
So I work with a local high school first robotics team, and last year they were programming everything in Java. So the idea with this thing, well, it's a robotics team, so we're learning how to wire up and do the hardware side of it, but we're also moving the whole team over to Python. So this little guy will look and feel just like the library that they have, Robot Pi, or the first robotics team. First robotics organization. It's been a lot of fun. Fortunately, it seems to die. It's happy.
All right. Any questions before we wrap this up? Go.
Yeah, how does that interface, how does the Python fit into the interface you're showing us? The web interface that you're showing us?
Oh. So somewhere was an export JSON, and it just like the JavaScript or whatever it was doing that GUI says, here's some JSON to download, and you click save, and it's got a file that's JSON. These things have a USB interface, so it looks like a file system on there. Drag and drop it, copy command it, or whatever onto that.
Basically, what moves from the IDE there to over here is a bunch of subscription lists. So any device publishes something to a CAN bus and has an ID attached to it. So it's basically some JSON that.
That's what happened with this. He was asking about the ID.
How does it tie it?
How does the, when we drag, you connected all those dots together on the screen, how does that happen? Like export. So. Can you imagine if there's on the web page an export button and download the file? Because otherwise I gotta check my password. I mean, if you want to come to the JavaScript meeting, I'll get someone to do the JavaScript. So, someone around here might have been responsible for writing the JavaScript.
I mean,
That's the JavaScript is what you write, but you'll be things in. For now.
Well, actually, so on this guy here is actually a class.
Huh. What do you use it for? What do you use it for, like an API or something? Or?
Yeah, so listen. So we got a few different things going on here. This guy can just be set up as a web server, or sorry, access point. And in the back there has a little controller that's another one of these, and then logs into here, it's a socket. And you can drive this little thing around and control mustaches. And some other nice people have built some other frameworks, like Flask. It's called Jinja. Is that correct? Like the
templates?
sorry?
That's templating.
Yeah, so it's also got a templating engine in there to generate some HTML.
Oh, what?
Are you using that for HTML or are you using that for big? Because that's too big for Jinja, like templates, big files.
Well, so I kind of just spun it up, but I think probably what it's going to be is just well, you kind of program some stuff in here and then
Hang on, back up. Which one was about Jinja? Someone else's project.
yeah.
I was just wondering if you were using Jinja, like, you said you were doing API, I was wondering if you were doing HTML or if you're doing big files.
He's not doing anything. Good Jinja.
Well, I'm writing some templates. Well, so I don't believe that Flask is, Jinja is the template. What's your Flask? Is this correct? Am I using the right words? Yeah. So,
You already.
yes.
Oh,
I was just wondering because it's like you're going to want to insert HTML and, you know, people use Jinja to insert variables in the web page there, but you must have big files like your settings and whatever. And a lot of the ops tools use Jinja to insert variables. I was just curious.
So as far as like this stuff that goes, the larger robot.py environment that's not just running on MicroPython has this thing called a driver station, and you can kind of get a web page that like says what's going on inside of this guy. What's the state of the mustache? Is he dancing or doing whatever? What's the state of the motors, temperatures, ABC values, whatever it is, and you just dump them out.
From the behavior, kind of like another key value store, or do you say state, I don't get it.
Yeah. I mean, it's Jinja. So like my first little stupid thing that I did with this, it's like, what do you do when you're learning a new language? I like made a little form and it fizz bumps. Just like put in a number and like how comes the web page just full of fizz bumps.
Yeah. Fair. Out of curiosity, does MicroPython have regular expression support?
Yes.
Sure, Python has support for it.
Well,
As long
going way back to that, what is Python?
as if the PSF or something would enforce this, whatever. Supposedly, Python includes the standard library. You cannot say this is Python if it doesn't have all the standard library features, modules, whatever. That is the Python standard library. MicroPython definitely doesn't have it, and not only does it not have it, it doesn't have room for most things. You end up with this little like build the thing that you want to load on here. What modules are you going to use for like? Say you're building a custom MicroPython, yeah, sure. It's more a like there's a whole bunch of MicroPython code, which is it's just Python code, kind of like the standard library, but there's a step of, in order to install it somewhere, you need to pull out the little things. You can't just go, here all is.
I have 32K flash. And so
The best you got is that
something.
we're done.
Like they said, 500K.
We're the middle.
A little. You could put RAM in it.
You guys want to talk? Ready to talk? You got questions? All right, that's it. We're done.
Cool.
Wait. Just in time.
Just one question, do you know what the libraries that are excluded are? Anything for document, anything?
So I did actually bump into, oh no, there was a library, wait, how did this go? I mean, the simple answer is, I don't know. I was going to recant a tale I had of, so like there's a library in Python where if you need to pack a bunch of data into like the first 3 bits come from this parameter, the next 2 bits are from this parameter, and end up, yeah, that sounds like it. So import struct, that's great. Except that the MicroPython implementation either doesn't exist or it is so big it would fit onto this. And so I had to write my own little like trimmed down version that kind of did the same thing. And it was kind of like, well, luckily what I need, I can do myself. But I remember like circling around trying to figure out, wait, what I'm doing, of course this is already done. Why am I writing the wheel? Well, the answer was because the CPython version of it is big, and the MicroPython version of it is like a trimmed down set of that trims some things I want to use.
You're probably gonna have X.
I would hope not.
So once again,
Needs of.
if it's just written in Python, it has it. You just have to decide, are you going to use up your precious space on
So I guess kind of to answer all these questions, there's MicroPython and then there's kind of like the PyCopy project. PyCopy tries to do all the other things that aren't in the built. So XML does exist, but it doesn't come predicted.
All right, we're done. No more questions. Got more questions? Ask them.
But Python comes with multi-like binary.
I know.
Find out.